Mung asked me to give a little bit of a history about cellular. Last time I talked, last year, I again gave the past history. This time I want to give a little, even though I have less time, just a very brief bit on how we got here and then where things are going, at least from my perspective. So let's see if this works. Oh, it was working before. Hold on. View. How do I do it? Full page?
Full screen.
Is that on this?
Yeah, full screen.
Oh, there, it's full screen mode. Okay.
Is it on? I'm sorry.
It doesn't matter. I can just I can do it manually.
I don't know
it's
why
okay.
it was working before. It's weird.
Okay. All right, so my career actually in wireless, I was where you were back in the late 90s. I just had graduated from my Ph.D. program. Are you guys undergrads or masters, Ph.D.s, or undergrads mostly, right? Okay, yeah. All right. So when I graduated in the late 90s, the late 90s was a very interesting time. At that point, there were two technologies that were really at their infancy, the internet and cellular. Today, we take both of those completely for granted, and we can't really imagine any digital technology without both of them. But it's hard to imagine that if you were wound back, and this is probably before many of you actually even had your own, you're probably all too young to know this, but at that time, these were still very early technologies, and people still couldn't appreciate how dramatic of a difference those would make in their lives. Let's see, page down, here we go. What we saw over the next decade was really the tremendous growth in both of those technologies and their merger together. That is really the unwiring of the internet. That is making the internet available to you wherever you are, and to wherever you are. I think people will look back at that decade and really see that decade as one of the really revolutionary eras in digital technology. Now, what I'm going to talk about here is really the top line, which is the developments in the cellular standards that enable that. Those are the beginning of that decade began with the emergence of 3G, and we later saw 4G. And I put some of these blue marks here to indicate some of the key milestones in that. But parallel to that, there were equally and perhaps more important developments. Also, we saw the introduction of Wi-Fi. You probably have always thought that Wi-Fi just always existed because you can't imagine having a computer or a cell phone without it. But in fact, that is actually a technology that only comes back to like the late 1990s. So prior to that, people didn't even have Wi-Fi. All right, so you might think that I grew up in the Stone Age or something, and maybe in some sense I did. But the parallel to that also is really the development of devices. And this is something that we're going to see that was incredibly important as well. That it wasn't just the network speeds, that there really needed to be a compelling device that you could experience the internet with. And really, actually, in many ways, the 3G technologies that began in 2000 and got significantly improved within a few years after that. But it was really the iPhone that really brought out the internet and made it such a tremendously valuable tool. So that really, the first one came out in 2007. That's a picture of it now. Of course, as Mung mentioned, they're just releasing the iPhone 5 right now, so it's 5 generations. Shortly after that were the first Android phones in 2008. But this was a really singular device that made people really feel that they could have mobile data on their fingertips. In fact, when I had started Flarion in 2000, we went to carriers at that point early, this like in 2001, 2, trying to sell the concept of wireless data. And the response we got from a lot of carriers was, well, who would ever want to check the internet on their mobile device? Now, you can't imagine someone thinking of that right now, but that was the mindset. And it was really Steve Jobs and his ability to have some kind of device where you could really see that, make that experience valuable, that was what made it so worthwhile. So, I'm just going to try in this, what do you have till 12:20 or something, maybe? 12:15?
20 past 12.
20 past 12 is total time. Okay. So in these like 15-20 minutes, I'm going to try to do two things. First of all, talk about this golden decade, if you like, about how we went from how the internet got unwired. And really that's a story about cellular technology existed prior to that decade, but it was primarily a voice service. And what we're going to see is how we make the internet go from voice to data. And within that, we're going to talk about a few topics. Probably, I think some things that Mung will talk about later in his class. The difference between circuit switched and packet switched, difference between peak rate and average rate, and so on. And that's all connected to what makes 3G and 4G valuable. The second part is I'm just going to give a little bit of speculative part on what's going to happen from here. This is not the end of this revolution, and in fact is really just, I think, the beginning, and where I think there's a lot of exciting technologies to happen. All right. So this one, again, if you have any questions, just really stop and answer, because it's better just to get things, answer things as they come up. So there are really two challenges for going from a voice-based system, which were the systems in the prior to the 1990s, going to a system that could actually do data. And that really is a result that data is fundamentally different than voice. The first aspect that is different is the issue of burstiness. When you're talking on a voice call, it's a relatively constant bit rate. All right. Now, so what happens is you talk into your cell phone, it gets converted into bits, and the number of bits per second is constant. That number is constant, and it's also relatively small. How small? So most cellular voice is at around like 8 to 12 kilobits per second. So if you want to design a system for voice, you want to have a very small pipe, if you like, allocated to each mobile, and have it so that you can stuff as many pipes in that connection at once, so you can serve the most number of users per base station. All right? So if you try to graph it, if you graph the data rate versus time, it will just look like a constant line. It's not exactly constant. They have something called voice activity detection when it tries to detect when you don't speak, and it shuts it off briefly to save a little bit of power. But otherwise it's relatively constant, so constant and small. Data, of course, is fundamentally different. What happens there is that you have a very bursty nature. Imagine that you're taking like web browsing. I click on a web page. When I click on that web page, I want to get a very, very high throughput. Why? Because I want to download that web page very quickly. How high? That could be in the megabits per second. So it could be orders of magnitude more than a voice call. So it's like when you download a web page, oh, you just saw it actually here, 2 megabits per second. Compare that to 8 or 12 kilobits per second. We're talking about 100 times. So what he was just showing there was like 100 users all calling at the same time. But then you stop. Most things are not like speed tests. You know, you're not constantly running them. You download the web page, and then as soon as you're done, you basically have an idle link because you're looking at the web page, and you don't need it. And so what the system has to do, of course, it means it has to. It's not like serving 100 users at a small rate continuously. It has to serve you the equivalent of 100 users at once, and then as soon as you're done, try to shift it over instead of serve another user. So that was the first major change that had to happen. Now, to understand why that was needed to make a radical change to the way systems were done, let's look back at a technology that existed prior to 2000. So GSM was the first 2G system. Mung mentioned what 2G is. 2G was the first evolution to digital voice. All right, so this became the global worldwide standard for voice. So that was GSM. So in GSM, it was designed for voice. So here's a very logical design for voice. What I'm going to do is I'm going to divide the frequency into these narrow 200 kilohertz channels, and then put time slots and give every person 1 out of 8 of these time slots. Right? Now this is a very small amount of data. Well, how is that small? Well, compare that to Wi-Fi. Wi-Fi is a bandwidth that's 20 megahertz, so it's 100 times wider. All right? And you can get it in principle for all the time, at least while you're using it. All right? So you can have a much higher rate. So this is a very small rate, but that's fine because all we need is a small pipe. 12.2 kilobits, you can actually transmit pretty efficiently in that little pipe. All right? So you transmit the small pipe, and the other part about this, that if you want to reallocate or deallocate, it's pretty slow. But that's okay because it's a med for voice. The idea is that you're going to make a call. It's going to take you time to dial the call. You're going to stay on it for like a minute probably or something, and then hang up. So, you know, if it takes hundreds of milliseconds, maybe even seconds to set up this little pipe and turn it down, that's okay. Because it's voice, you're not going to notice it in the long run of the call. Now, beginning actually, it was even prior to 1990, before the internet, they actually wanted to introduce data services. All right. Now, when they wanted to introduce it for other things, just like silly things like voice, basically equivalents to SMS and stuff like this. And there was actually, I remember even going to conferences at that time, people were saying, well, people maybe don't need the internet, maybe SMS is just enough, for example. These were all the idiot things that engineers like me and myself thought about at that time. So they said, well, you can still maybe do data. There's two problems with it. I said it's bursty and there's a peak rate problem. Well, at least the peak rate we could solve, or at least a little bit. When they went to this 2.5G, which is what Meng mentioned, you just maybe give the guy more of these time slots. So you can go from this 9.6 kilobits, you can go to n times 9.6, and you can actually maybe squeeze a little bit more into these time slots. So you can get into around 40, 50 kilobits per second range just by dumping these in there. So that was what was called edge. So how do you know if your phone is on edge? Sometimes you'll see it. It might just say E on it if you're on AT&T. If it says, if you've noticed that E stands for edge. All right, it's called hands, whatever. It doesn't matter what it stands for. So that's how you do it. But you can see some problems with it. First of all, what happens with data is bursty. So if I allocate you a bigger pipe, you're going to want to allocate it to your peak rate. So when you say download on your phone, all right, so you say, okay, you need a lot of data rate, so let me allocate you lots of time slots. But then you don't use it, and they go to waste. Why do they go to waste? Because it wasn't designed to quickly move those time slots from one user to another user. All right. So this could handle the peak rate a little bit, not great by these days. It was maybe 50, 60 kilobits per second. All right. But so it wasn't a great peak rate, and it still had this burstiness problem that was in fact wasteful. Probably if you got allocated 50 kilobits per second, you're probably using only a fraction of that, and you can't let any other user use them. All right. So what happens here is you get a data burst, but all these blue time slots here go completely wasted. Does everyone understand that? So you allocate all these slots, but you use it just for these parts, and these go wasted. So it's not a great peak rate, and it's pretty wasteful. Now, it's when 3G came out, actually in 2000, or actually what was called the Release 99, it wasn't also really a solution for data. All right. When people think about it today, it's synonymous with data, but at the time it was really just to use this CDMA technology, which Meng will talk about later, to enhance the voice capacity. But it was still a fundamentally circuit switched concept. All right. So you just allocated not time slots, you allocated some other type of channel, but you allocated in some fixed way. So the first key revolution came in about a few years later, in 2005, what was called high-speed downlink packet access, or HSDPA. How many people have seen H on their phone? Okay, so that's if this won't apply if you're a Verizon customer. Verizon had an alternative system. You'll see it called EVDO, or it may just say EV or something like that. Maybe it just says 3G. All right, if Verizon it says 3G, it's a similar system to this. So H just stands for HSD. Well, it stands for HSPA, speed packet access. The downlink part was this. So when it's connected on that, it does this. And this was a system, really the first commercial system that was really designed for data. How does it work? What I'm going to do is I'm going to divide, just like the GSM, I'm going to divide into time slots. But first of all, the time slots are a lot wider in frequency. They're about 3.84 megahertz. So there's more than 10, 15 times larger than that GSM time slot. But I'm not going to pre-assign any of these time slots. So I'm just going to leave them open, and I'm going to be able to schedule them on the fly. All right? What does that mean? Well, suppose I have packets arriving for these mobiles, because it's a packet system, not a circuit switch system. So if some green packets arrive for, say, mobile 1, I can schedule those to user 1 and user 1. And as soon as I'm done with that, I can schedule to a completely different user in the next time slot. And then again, schedule to another user in the third time slot. So this way, you have a very low delay to actually transfer data, to transfer the resources from one user to another. We're going to talk a lot in this class about the idea of resource allocation. In some sense, this power control problem is a resource allocation problem. You're allocating power between one user and another. A lot of what we want for data is about the speed of that allocation, right? How fast you can allocate those resources back and forth. And that was the key insight into 3G data. All right, that was so that was introduced in how fast? Well, these time slots are 2 milliseconds. That means if a packet arrives, in principle, within 2 seconds, I can still start transmitting it out. So much lower delay. In comparison, it took like hundreds of milliseconds to reallocate resources in edge. So this was a significantly lower delay, much higher peak rate, and much better utilization of the channel. Now that being said, the iPhone, someone mentioned, actually came out in just using 2G. And it came out in 2007, 4 years after this technology was available. Does anyone know why Steve Jobs didn't pick to go on 3G? It was power consumption, right? He was very worried that the phones would burn a lot of battery life, right? And it's something that's actually influenced. You notice that iPhone 5 wasn't even the first phone out with 5G, with 4G. It's just that when you go to higher bandwidths, they eat a lot of power, and he was worried that it would burn a lot of battery life. And so it took a little while for the battery life to come to an acceptable level. Yeah.
How did they manage to switch it more quickly between users?
So what happens is you're still transmitting. All you need to do is you just put a little channel, another channel, which tells you who this time slot is assigned to. All right. So every time you listen to all the time slots, so your mobile is still running all the time. So that's why it eats a lot of power. You have to listen to this whole bandwidth the entire time, and then you just look. You'll say your mobile 1. You look at the sort of a small signal in here which says, is this slot for me? And say, oh, it is for me, I'll decode it. But then you look at this one and say, and everybody has to decode this. And they'll all look at, is this for me? And if it's not for me, then they just don't decode it, they ignore it. But they have to eat the power this power while constantly listening to it. That's actually how Wi-Fi works too. How does your laptop know the packet for it? Well, the base access point sends a packet out. It has your address in it. All right. It's imagine like I down a letter. I write your name on it, but I hold it up and say, everybody look at this letter. Who's this for? All right. And then you all look at that and say, oh, this is for Jean. And then Jean will take it and I'll give it to you. All right. So that's how it works. There's a kind of address on it. And we went from much higher, went from 50, 60 kilobits up to 14 or 7 was probably more realistic in the early versions. And today you get 40 megabits and even higher. All right, on it, in principle, the peak rate. 4G expanded this further in 2 ways. We got even a higher bandwidth in principle, although most carriers run at a bandwidth that's not that much larger than 3G, but it can go up to like 20 megahertz. But it also allowed this division in frequency, and it divided this through something called orthogonal frequency division multiple access. It's basically the same. You have divisions in time and frequency, and you can assign people arbitrarily blocks within this. So what that allowed is sort of further granularity of the channel. The problem in 3G is that kind of these minimum blocks are still pretty large. So if you have a small packet to send, it gets kind of wasted. Right? In 4G, you could send a lot of small packets as well, and those are things for like TCP ACKs and for other, if you did want to still send voice and other things like that, could be put into these parts, and it would allow much more flexible scheduling. It also introduced other parts here that you could coordinate transmissions across cells. You could say, I'm going to transmit on frequency 1, a neighboring cell could say, I'm not going to transmit on that frequency. And it also had changes which are independent of this, things like what Mung mentioned about going to an all IP network. All right. Oh my God. Okay. I've like almost blown on my whole time. All right. I didn't want to go to end, although probably I should go to end. Okay. Let's just talk about this. The second challenge for voice, sorting down data, was try to improve the reliability of the service. Right? And so what had to happen there was you needed some mechanism. So if data is much more sensitive to needing a channel that's reliable. All right, reliable means when you transmit voice. Actually, I'll just say this and without going, I won't have time into this. When you transmit voice is tolerable to some levels of errors. If you lose some voice packets once in a while, you just might sense a slight degradation in the quality. Data, on the other hand, you need perfect reliability or very high levels of reliability for there to be a reasonable connection. And so you need other mechanisms to try to improve the reliability, which is fundamentally hard in a wireless channel because wireless is kind of uniquely susceptible to problems of data because of a process called fading. So those were other parts that were introduced in 3G and 4G to get around that in a way that's delay sensitive. Because I'm running out of time, I will just leave you with that. So let's just talk my last few minutes here, 5 minutes, to talk about what's next. If I have time, I'll go back. Sorry, I should have. So in some sense, cellular technology right now is really a victim of its own success. What we've seen is a huge growth in data, but that growth is really going unabated. The more people experience, the more people they want it. And the more people experience, the more they want. And how much is it growing? Approximately doubling every year. Now think about that from the perspective of the carrier. If the cost structure for delivering data remained the same, they would have to basically charge you double the amount to get the same amount of data. Of course, you're not willing to have your phone bill double every year. Maybe you're willing to pay a little more because the service is getting better, but not double. So they have to find radically cheaper ways to try to deliver the same amount of data. All right. We'll also talk about ways, I think, Mel, you're going to talk about a whole lecture about pricing and things like this, right? About maybe the pricing plans to incentivize people to use their data better. But let's just talk a little about the technological solutions that you can do. So there are sort of two key solutions. I'll just skip to this one here. One idea is to place just many, many more cell towers. Right? And this has been a process that's been happening over the last at least 20 years. So if you look back at the traditional macro cellular tower, you might see these on the highway. These are large towers that sit up maybe near a highway with many antennas on top of them. Maybe they could be 20, 30 meters high. Right? They were already, what was going to what we call metro cell sites. These are things on just the sides of buildings in more dense areas. And now we're thinking about things what are called like femtocells. These are very small personal base stations that can be manufactured at almost the cost of just a Wi-Fi access point or like a commercial grade Wi-Fi access point. On top of that, they can actually be deployed inside a subscriber's home or maybe in an enterprise. So for example, Princeton University could put this on their campus, and then the operator wouldn't even have to run and operate that cell. So you can buy many more cell towers at a much cheaper rate. How much cheaper? These are around the neighborhood of $100,000 when first a few years ago. These could be in the neighborhood of $1,000. So we're getting orders of magnitude cheaper. The other part I'll just mention, just one other technology which I think is an area that's of just interest to me. There are many ideas, but one is the idea to expand into new frequencies. So cellular signals, just like all types of radio wave communication, operate in a frequency band, right? Just like you tune in your AM or FM radio. All cellular communication sits in a very narrow band between 0 and 3 gigahertz, pretty much. Right? That's all today. But in fact, there's a huge amount of available spectrum available in the regions above that, up to say 300 gigahertz. This is sometimes called the millimeter wave space because that's the wavelength of those transmissions. This part here, if it can be used in a viable way in cellular technologies, could expand up the capacity by orders of maybe 200 times because there's much more spectrum. That has other problems, this space, because it has some problems with the propagation. But since the cells are becoming much closer together, this might actually be a viable option to expand the capacity dramatically. All right, let me just say a couple last things. There are many other possibilities to see. Some are on the devices. There are things that you're going to see. There's actually, with the iPhone 5, there was an excellent article just on the New York Times about just the evolution and talked about, maybe I send you guys a link to it, about maybe the iPhone 5 seems kind of incremental, but in fact, if you even just look at the series of incremental reductions and improvements that are coming up, that there's still pretty dramatic increase of improvements of devices that's happened over the last 5 years. And I think we're also going to see continue more other types of improvements. One might be some radical things. This was something that came out of Nokia's labs right now. They're experimenting with these flexible electronics that you can have wearable computers, or you could expand them out so that you can get a display that opens up. You're going to have a lot more new interfaces into devices, or gestural devices, or 3D, more sensors, more cameras. There's other things people talking about in terms of augmented reality, and other ways that the network itself can be improved by trying to make these other improvements that I've mentioned, and also maybe the vertical integrated model for the carriers, the way they're deployed, that might end up changing too. So let's just wrap this up with a few comments. So the mobility has really revolutionized the digital era. It's really hard to imagine any digital technology that hasn't been fundamentally changed by the ability of being mobile. And that's not just voice communication, of course, but it's internet communication, it's gaming, it's entertainment, it's office, it's navigation. All these things can benefit from connectivity to the web. There were many technological advances to make that happen. I just mentioned two. But actually, the biggest change was actually seeing the value of mobility in the first place. The concept that mobile data is valuable was actually really the key part. The consumer adoption needed combined progress. It needed the enabling technology of networks, so things like what you're studying here, but also devices and applications that could make it worthwhile. I think we're going to see, this is really, like I said, just the beginning of the full impact of mobile era. We'll see that in this last decade as a tremendously important one, but I think there's many, many more things to come, and maybe from studying this kind of class, you'll be part of that.